Well, thank you everyone for standing by, and welcome to the second webinar of our winter series, Stormwater Management and Climate Change, Implications for the Great Lakes Region. These webinars are an initiative of the Ohio State University Climate Change Outreach Team. With this webinar, we worked in collaboration with the Great Lakes Regional Water Program, the Ohio Coastal Training Program, USDA, and the NOAA Great Lakes Sea Grant Network. The OSU Climate Change Outreach Team is a multi-departmental effort led by OSU Extension, Ohio Sea Grant, and 6 other OSU departments to help us localize the climate change issue for Ohioans and Great Lakes residents. I am Ann Baird from Ohio State University Extension and the School of Environment and Natural Resources. Just a few logistical aspects. During our presentation, all participants will be in listen-only mode. Afterwards, around 12:30, we will conduct a question and answer session. If you would like to ask a question during the presentation, please just type it in the chat feature located on the lower right-hand side of your screen. Please submit your questions at any time during the webinar. I'll be organizing them throughout the presentation and posing your question to our speaker at the end. We have over 100 participants on this webinar, a great diverse group representing both public and private organizations around the Great Lakes region. Feel free to keep those questions coming, and then we'll have a lively Q&A session. As a reminder, this webinar is being recorded and will be posted on our website for later viewing. We will have a short online survey posted in the chat feature for you to go to at the end of the webinar, and we would appreciate you taking the time to fill it out. Without any further delay, I would like to introduce our speaker, David Liebl. David is a statewide outreach specialist for the University of Wisconsin Cooperative Extension. David is a member of the Wisconsin Initiative on Climate Change Impact Science Council, where he chairs both the Outreach Committee, the Stormwater, and Adaptation Working Groups. And with that, I want to say welcome to David.
Well, thank you, Ann, and welcome everybody. I'm glad you could join us today. I hope this is an interesting discussion for everyone. We're going to take a look at stormwater management and climate change and what we've learned in Wisconsin, primarily working with the Wisconsin Initiative on Climate Change Impacts. And I hope that what we see today will be applicable generally throughout the Great Lakes region. It's going to be a fairly technical talk. I don't want anyone to be put off or intimidated by that. And just to let everyone know that the slides from today's presentation will be available once the program is archived, so you'll be able to go back and look at a few of the figures. I just want to point out that support for this program has been provided by a number of agencies, including the NOAA Sectors Applications Research Program Water Focus. And so I want to express our appreciation for being able to move forward with that. Today, we're going to take a look at Wisconsin's changing climate, what we've learned about it through the Wisconsin Initiative on Climate Change Impacts, and then how that pertains to stormwater management and some of the impacts of precipitation on from our changing climate and how we as a society might adapt to that. We'll be looking at a variety of figures like you see on the right, which show a historical average increase in temperature and precipitation across Wisconsin. And these are quite interesting. I think you'll find as we discuss these, you'll get a little bit better feel for why we think this is such an important issue. WICI is a program that was pulled together by the Department of Natural Resources and the Nelson Institute for Environmental Studies on the UW-Madison campus. It's a very interdisciplinary effort. It has a number of working groups looking at different aspects of climate, and its goal is to really assess what climate's impacts will be on the state and how we as a society might adapt to them. Brian, I don't know if there's anything we can do about this, but you seem to have the PDF slides and not the PowerPoint slides up. I'll just keep talking, and if we can change that as we go along, that'll be great. As most of us know, what really concerns humans about climate is weather and the impacts of weather on our built environment and the natural environment. And these are just some examples of what we see day in and day out throughout the year. except probably for those two guys floating on that ice floe doing their ice fishing right at the end of the season. That's a fairly unusual thing that we might see some more of. High water impacts are something that we have recently found that are more of a problem, especially in the western Great Lakes region. This is an example of a storm event that took place in 2008 over the period of a week and a half or 2 weeks. You can see from the radar images there that there was 12 to 14 inches of rainfall over south central Wisconsin during that time period. That led to some serious overland flooding. We had two major interstate systems that were closed for days because the roadways were underwater. In addition, as you can see, substantial sewer overflows into the lakes and streams, and a large number of rural drinking water wells that were contaminated by surface water and by groundwater flooding from that event. Overall, $34 million in damage claims were paid by FEMA just during that storm event. So these types of impacts are real and significant and something that we are growing more concerned about. The way that we've approached this problem at WICI is to begin by taking a look at climate historically in Wisconsin to see if we can understand the nature of these changes in variability and how our current situation is in that context. And it's been, we have quite a long record in Wisconsin of measuring rainfall, temperature, and so forth, but you'll see from most of our slides that it's really only in the last 50 years or so that we have a complete record from all of Wisconsin's cooperative weather stations that allows us to use a statistical approach to analyzing this data. Here are some fairly typical indicators of climate change. On the top left, you'll see is a graph of the change in the global atmospheric temperature anomaly. This has been in the press quite a bit lately from the IPCC. But more locally, we have a chart here that shows the duration of ice cover on Lake Mendota in Madison, Wisconsin from 1855 to 2008. And as you look at something that's just a little closer to home, it's quite dramatic in showing the reduction in the number of days that we have ice cover over the lake, and that most of the longest periods of ice over are very early in this century or at the end of the 1800s, and the shortest days are grouping, as you can see, more recently around this last couple of 3 decades. So this would be a good indicator, I think, of what we're seeing in terms of a way of measuring overall winter temperature increase. On the lower left here is a annual precipitation record for Madison from 1869 to 2008. And you may see from this averaging line here that seems to be a slight rise in the amount of average annual temperature. Well, further on in today's talk, when I take away this gray box, you'll see that the longer your record, the better you are at identifying trends in climate. And this is a challenge that we have for stormwater management in particular, is how to identify and validate those trends. So let's summarize what WICI has found for recent historic climate in Wisconsin. And again, this is the 1950 to 2006 National Weather Service co-op station records. And you can see from the figure here that there's a disproportionate increase in temperature from the southeast part of the state to the northwest part of the state, but it's averaging about 1.5 degrees during that time period. Winter days and winter nights showing a little bit more warming than the rest of the time. And the number of below zero nights, as you can see, has dropped by almost 20 nights, which is good news for everyone but the skiers and the snowmobilers up in northwestern Wisconsin. Precipitation, on the other hand, tends to be a little less uniform. On the left, we can see annual average precipitation in inches over the same time period, but it ranges pretty dramatically from an increase of 7 inches to a decrease in 4 inches, which reflects drought conditions that have taken place in northern Wisconsin over the last several decades. On the right, we have an increase in the amount of 2-inch rainfall events from that same period. Again, 3.5 days increase to 1.5 days decrease. That's a lot of local variability. And it's important to keep in mind that as we measure precipitation in particular, we can't make generalizations about an area even as large as the state of Wisconsin, much less for the entire Great Lakes Basin. We, of course, would be happy to be able to tell you that we can see into the future and tell you exactly what's going to be happening with climate. All over the world, people are wondering about climate and its impacts for the future. And as you all know, I think the IPCC has done a tremendous amount of work trying to model as clearly as possible what we expect the shifts in climate to be across the globe in the next 50 to 100 years. Just as a review of that approach, using what are called general circulation models to simulate climate on fairly large scales across the continents and the ocean. The IPCC working groups have come up with a number of 15 or 16 different general circulation models, all trying to do the best they can to project how climate is going to act based on what we know today. What Wiki has done with that information is to take 14 of those models and try and downscale them so that the resolution of the projections are scaled to the size of the state of Wisconsin. And on the left figure, you can see the grid cell size for the IPCC GCMs. And on the right is the statistically downscaled grid cell size that is used for the Wiki climate projections. Now, the approach that was taken here was to, for each of the individual GCMs, verify, or what is known as statistically debias, the data for the historical period of record that we know. So in other words, you're starting all those global circulation models off with the same data, the same conditions as you run them off into the future. And then using those 14 models, generating a statistical range of probable climate change for temperature and precipitation and so forth. And what that looks like, for example, for temperature, on the left shows the annual average increase projected for the period 1980 to 2055 for the state of Wisconsin. Again, 6.5 or so to 7 degrees Fahrenheit increase over that period. That's a significant warming trend. On the right, though, is a more detailed description of the data that was used to create that figure. The red line, or the median line, shows the average between not all of the 14, but the 14 that fall below the 90% or above the 10% percentile confidence limit. And so throwing out the outliers here, this range shows how much you might expect that annual average to vary month to month into the future for that time period. Now, that's something that is pretty reasonable for temperature, but as we'll see for precipitation, that range itself can be problematic for projecting what we can expect from climate impacts. The farther out we get into the future, of course, those models tend to diverge from one another. And by the time we get to the end of the century, even though we're showing an average, a mean or an average increase in about 10 degrees Fahrenheit across the state, it's plus or minus 4 degrees. So it's a fairly large range. And at least for stormwater management and precipitation analysis, we feel that we'd like to limit our reliance on those long-range projections into something that's just a little bit closer to the next 50 years or so and try and reduce that uncertainty as much as we can. So let's take a look at what some of the projected precipitation is using this downscaling approach with the 14 general circulation models. It looks to be about 1.25 to 2.25 inches in increase in the annual average for Wisconsin over the next 40 to 50 years, and about 2 to 3 days per decade of additional 2-inch rainfall events during that period. And those are, I think, from the point of view of most stormwater managers, fairly modest increases, certainly manageable, and something that even looking at the range of probability, we think that we can deal with as it's coming along. More interesting, though, is the seasonal aspect of what is happening. Even though water is increasing in terms of winter precipitation, snow depth is decreasing pretty dramatically during that same time. And when you think about what we said earlier about temperature, both an average annual increase and warming in wintertime, it certainly would make sense that you would have less snowfall and more liquid precipitation during the wintertime. And this is just a little bit more fine analysis of that from work that we've been doing here at Madison. And this shows the percentage increase in precipitation as rainfall versus snowfall, comparing the historic record with the projected record for the months of November through March. And as you can see, there's some fairly dramatic increases in the amount of rainfall versus snowfall that we are looking at in the near future. And over on the right in the table, note that even though that these percentages are quite high, the actual amount of rainfall is not as dramatic as you might see in the summertime. So we're talking about a change in the character of our precipitation more than we are actually talking in a change in the amount of precipitation that we're going to be having during that period. So just to try and summarize briefly, what are we expecting in terms of Wisconsin's projected climate as far as stormwater management is concerned? Well, as I said, warming nighttime and winter temperatures, significant increases we saw of rain during winter, reduced snow cover, and a moderate increase in the frequency and intensity of precipitation, but not something that is dramatic. So this still leaves us with a big question in terms of what this means for weather. Climate, of course, being something that we try and understand over a period of decades generally. Weather being what we have to manage day in and day out, both personally and for whatever infrastructure or so forth that we need to be managing. Let's take a look at that question of changing patterns of precipitation. As I said, more frequent and intense rainfall in winter and spring, we think that's going to lead to both more high water events or early spring flooding, and interestingly, we think we'll see more groundwater recharge. Lots of recharge takes place in a time period when there is either frost off the ground or shallow frost, snow melt and rainfall combining during a period when the plants are not green and so there's very little transpiration. And that groundwater recharge is something that we're very concerned about. In Wisconsin, as you can see on the right, we have a very high vulnerability from high water events during winter and spring. You're looking at the time of year or the season for the top 10% peak flows for these stream gauges throughout Wisconsin, the green being springtime, and as I think no one would be surprised to see, many of these areas see their highest flow rates in the spring when we're talking about beginning to get more runoff and more rainfall. Another impact of this change in seasonality would be sanitary sewer overflows. This is from the Milwaukee metropolitan area, over which a large portion of the system is a combined system of both stormwater and sanitary sewers. And here under the arrows are the examples over the last 5 years where we've had substantial combined sewer overflows that were the result of spring rainfall events. And you'll notice that those are not the major rainfalls that were causing CSOs in terms of inches of rain. However, you have a period when you have both snowmelt and rainfall taking place, which means that your runoff could exceed what you would expect for the amount of rainfall that you get if you have rain falling over snow. And you also have the high groundwater effect that I mentioned, causing inflow and infiltration to these systems. And so we expect that this change in seasonality will have an impact on our ability to manage our sanitary sewer discharge to our lakes and streams. Another question that we've come up with is whether or not we're seeing a changing pattern in rainfall itself, not just in the season, but in the way the storms are coming. And if you look at the graph on the upper left, this is the number of rainfall events that broke a weather station record or came within 90% of breaking a record for each of the decades from 1950 to 2000. And so we can see that, 3, 3, 3, jumping up to 4, jumping up to 6. This might indicate that there's an increase in the number of these record storms that we're seeing in the recent future. And you remember that the plot that I showed very early on of the annual total precipitation in Madison, on the right is the period of record that's shown in the graph on the left, and we looked at this long rising curve here. Well, going back further into the record, into the late 1800s, notice how much rainfall we had in Wisconsin, in Madison at that time. We really do wish that our rain gauge system was more complete that far back in time. It would be very helpful in terms of developing statistics. So we don't really know at this point if we're looking at a gradual increase, the beginning of a steep increase like this, or a trend that we expect to rise more or less steadily into the future. There are decadal cycles that come into play here, different oscillations in the weather patterns that combine and give us these few years together of very heavy rainfall. In any case, what we're looking at in terms of stormwater management is how to manage the rainfall that we can reasonably expect to happen in the next 10 to 20 years. And we've taken an approach to that we think is robust and will be helpful for folks that are trying to do this elsewhere in the Great Lakes system. Many of you may not be familiar with where the rainfall statistics come from that are used to design our stormwater management infrastructure. Technical paper 40 comes out of the period 1938 to 1958. And if you look at these two graphs, the one on the left, again, is a representation of that largest daily rainfall for Madison, Wisconsin over that time period. And on the right is the flow of the Mississippi River at Clinton, Iowa, which is downstream of Wisconsin. Both of these show that a period that we are now using for our rainfall statistics seems to be in a period that was relatively dry over the last 100 to 150 years. And the question that we're asking is, by using these statistics, have we been designing our stormwater management infrastructure for a climate that is historically dry or not? Unfortunately, moving forward, we're faced again with this question of uncertainty. The graph on the left shows us the different projections for summer rainfall from the 14 different general circulation models that were used for the wiki analysis. And as you can see, for June, July, August, and September, there's a great deal of disagreement on what is going to be happening in terms of monthly precipitation in the next 50 years or so. From this graph, you couldn't really tell if we were expecting wetter or drier summers. On the right is a projection based on the same data, looking at the size of the 100-year 24-hour storm event over the course of the next century. And as you can see, the farther we get out into the future, the broader the spread between those events, the more difficult it is to come up with a mean that is significant or meaningful in terms of stormwater management planning. You're kind of left with the choice of, do you think it's going to be 6 or do you think it's going to be 9? These are not really that confidence inspiring if you're designing a multi-million-dollar stormwater management system. Now, one way to approach this is to upgrade our statistics. Remember that the TP40 is quite old at this point, and NOAA is in the process of doing that for the Midwest states. As you can see, this area of the mid-tier states, Indiana, Illinois, Ohio, Pennsylvania, this has been done already. The western Great Lakes states and the rest of the Midwest we expect to be due out in May of 2012. This increased statistics may give us a handle on how we should be designing and managing our stormwater systems. NOAA Atlas 14, which updates TP40, uses more stations of record, a longer period of record, and a revised statistical method to give a more precise statistical and geographical idea of what we can expect for different types of storm events. And just as an example, this is what you would get from NOAA Atlas 14 for South Beloit, Illinois, for a 30-minute rainfall. And TP40 would have given you this isodal map that you would have had to interpolate this general area from these different adjoining areas. So it's going to be much more precise and much more useful for designing and regulating stormwater management. We asked the question, of course, well, if NOAA Atlas had been completed already for Wisconsin, what would the effect be on the way that we look at our statistics? Unfortunately, Davis, Todd, and others at Purdue have already done that in terms of looking at what the increase in rainfall frequency and magnitude was for the areas that I showed you where NOAA Atlas had been completed already. We're looking at some fairly modest changes in these smaller storm events for these different states. Although when we start getting into the larger storm events, we're seeing some pretty big variability, some of which we think represents an improvement in statistics, also maybe some urbanization effects. But all of this is reasonably manageable. I guess the question that we have is that going to be enough as our climate seems to be changing in the future? So what we've done is taken a look again at the historic rainfall. Again, this is data from weather stations of events that have occurred, and so there's really no statistical uncertainty or projection involved. And one of the things that we were interested in seeing was for a fairly large 24-hour event, 5 inches, which is around the 100-year event for most of Wisconsin, how often has that occurred at the weather stations that we have records for? And so this is, again, 1950 to 2007. The size of the circle is a rough indicator of the number of events. The color of the circle, again, an indicator of the overall size of the event. I don't think it's really important for us to look at any of those locations specifically, except to say that you'll notice a large part of Wisconsin doesn't really seem to have experienced too many of those major storm events. And one of the questions that we're asking is, are these communities prepared to manage those type of storms? Much of the evaluation of stormwater management runoff and flooding is based on personal experience of the managers of these systems, and if they haven't seen anything larger than a 3 or 4 inch storm event, how are they going to manage for a 100-year event? And then there are the really, really large storms. These are the 7-day 9-inch events for that same period, so a week of heavy rainfall. Notice that they're very rare. Notice also that we have some cases here where you have a storm system that causes these types of rainfalls over a fairly large geographic area, and that those rainfalls are really of two types. One is from the same storm event in the orange that we're looking at for Viroqua over here in western Wisconsin. A very, very heavy 24-hour rainfall followed by almost no rainfall at all. On the far eastern end of that storm system in Watertown, we've got rainfall and then rainfall and then rainfall again. And depending on whether your system relies on moving flood flows or you have BMPs that attenuate or store water, and whether or not you're in a very hilly terrain as it is over here in the west, or whether you're in a flat terrain that doesn't drain very easily, these different types of storm events can have dramatically different impacts on a community. And we question whether any communities are prepared for these events. So here are some things that we've concluded from looking at this situation, both the historic and the projected stormwater impacts for Wisconsin that we think are probably valuable for the rest of the Great Lakes as well. Obviously, our statistics need to be updated. We have to rely on those for our design criteria. We think that the uncertainty in our precipitation projections really does constrain our infrastructure design. Very few managers are going to spend millions of dollars to anticipate events that have a probability distribution function of plus or minus 90%. So what we're more interested in doing is looking at where we have a lot of confidence in, for example, the change in the seasonality of the rainfall, and understanding impacts and vulnerabilities from these heavy rainfalls that we've experienced in the past as a way of identifying how communities can implement adaptation for climate events that we think may occur. So let's talk about adaptation briefly. As you all know, I think mitigation is something that is focused primarily on to minimizing the causes of climate change, and that's not really where Wiki is focused. We're focused on the fact that we expect change to occur and we need to be able to manage those impacts. And because climate presents a wide variety of hazards and of severity and likelihood, I think everybody's probably seen a silt fence overflow like the one on the left. But on the right, we have an impoundment, Lake Delton, that completely breached its berm and drained into the Wisconsin River. That's more severe and less likely, but we need to be able to manage for both of those. So I'm going to talk about some impacts and adaptation strategies briefly that we have found through the Wiki working group process. And these, I think, are going to be generally applicable to the Great Lakes region. Soil loss from changing precipitation in the springtime can be dramatic. And the thing that struck us is that the Soil Conservation Working Group said that we have the practices in place and we know how to do those practices. And if we were to do those practices, we could minimize that soil loss pretty dramatically. And these are just some examples of the types of agronomic practices that are, I think, well understood and accepted in terms of reducing soil loss. Groundwater flooding, I mentioned that we expect an increase in groundwater flooding, and this is when the groundwater table rises above the surface elevation. And you see here pictures of areas that are internally drained that don't have a natural outlet, where people have built that in recent years, because of the change in seasonality of the precipitation, groundwater has come to the surface and flooded their property. And it would be a good idea, we think, for communities to have mapped hydric soils that are indicators of previous wetlands and high groundwater. And in fact, Wisconsin has a very good program for identifying where those hydric soils are located. On the other hand, however, we have to keep in mind that just because you know there's a problem or might be a problem in the future, that doesn't prevent somebody from putting a subdivision there. And so the Stormwater Working Group of Wiki feels that it's very important that there be some way for planning and zoning people to be able to identify those areas and prohibit the type of development that leads to these types of damages and flooding. High water events, as I mentioned before, are common throughout the Great Lakes region. Upper left is the Reedsburg wastewater treatment plant that did not have a high enough containment dike around it to prevent the Baraboo River from flooding that plant and shutting it down. Other examples, I think, are familiar to folks. How about adaptation to those types of high water events? Well, planning 25 or 50 years out is very, very challenging, and this is something that we think we need to learn how to manage. We're looking at the bottom at a plan to take a neighborhood in south central Milwaukee and raise residential buildings to recreate a floodplain to manage some of the high urban stormwater flows that you're seeing on the left-hand side of that picture. Now, that type of effort requires incredible political support, as you might imagine. And the only way that you can really effectively convince people that this is going to work and alleviate a problem is to be able to simulate what's going to happen for different types of rainfall events in a watershed like that one. And so we think that using those type of hydrologic simulations are going to be very effective tools for stormwater management planning in light of what we're looking at in terms of the climate and weather. Something else that we've seen recently is that on the upper right is the road crossing in rural Wisconsin, where we got a call to come in and take a look at why above here we were getting tremendous flooding in this area behind this road crossing. And for those of you that are familiar with this type of structure, you'll notice that this grass and sediment here would tend to indicate that there's not been very much maintenance done on this particular conveyance recently, and that this was actually clogging up this drain, causing the flooding upstream, and could be very easily remedied. So communities that have or we think are likely to have large storm events are in a good position to be able to go out and identify those types of vulnerabilities. And here's a list of the types of things that they should be looking at and determine whether or not the risk from increased rainfall events is likely to carry with it a cost or a risk to public safety that would justify making an investment in improving infrastructure, and certainly justify an improved approach to maintenance of some of these systems. Sanitary sewer overflows, which I mentioned a little bit earlier. As we all know, these are a source of pathogens and nutrients to the lakes and streams, the Great Lakes in particular. Sandra McClellan's lab at the University of Wisconsin-Milwaukee has been doing a really good job of a fine analysis of what the Milwaukee system is capable of in terms of transporting bacteria, for example, into Lake Michigan to the beaches. And we found that about 75% of Wisconsin's sanitary sewer overflows are a direct result of precipitation, either surface runoff entering the systems as inflow or groundwater seepage as infiltration. And some of the things that we would be able to do to help with this would be to, for example, disconnect stormwater inputs. And on the upper right, you see a cistern that's being used to collect roof water for later use as irrigation. However, that may not be politically feasible. In Milwaukee, they've just backed away from requiring residences on the system to disconnect all of their roof water from the sanitary sewer drains because of the cost, which was estimated to be about $7,500 per household. Infiltration from groundwater is really a sanitary sewer system maintenance issue. They can be tightened up to reduce that amount of infiltration. Temporary storage is being used by some municipalities to hold large storm events. Milwaukee does that. Racine does that. Again, you can spend billions of dollars on that, and you're still going to have sanitary sewer overflows. One of the more cost-effective approaches, we think, is to educate homeowners on on how to prevent runoff inflow into their basements and their floor drains, how to make sure that sump pump discharges do not go into the sanitary system. And certainly wastewater treatment plants need to be planning for those extreme events like Reedsburg experienced. So what about coastal vulnerabilities? I know folks in the Great Lakes are very concerned about water quality. And it's interesting, I think, to think about where climate is going to have the largest impact on some of these estuarine systems and our nearshore coastal waters. And if you look at this map, the size of the watershed for the city of Green Bay, for the Fox River that runs through the city of Green Bay into Green Bay itself, it seems clear that upland stormwater impacts are going to be a major factor in on these systems. And here are some examples of the vulnerabilities, both economic vulnerabilities and environmental vulnerabilities. None of these should be surprising. We already experience these now from much of our coastal areas. More interesting, I think, are areas where we have problems with bluff recession, freeze-thaw cycles, late winter, early spring rainfall, increasing some of that bluff recession. And the idea that as the Great Lakes rise and fall, people are tending to build out towards the ordinary high water mark or beyond it. And with some of the heavy rainfalls that we've seen and the inevitable temporary rise in lake levels that we expect, we may see flooding of areas that were previously developed with the idea that they would be free from that type of flooding problem. So those are some examples of impacts, adaptation strategies, vulnerabilities that we see from precipitation in Wisconsin and certainly also applicable to the Great Lakes region. How are we going to cope with this in the future? Well, we've identified a number of gaps that we think need to be filled if we're going to be able to successfully manage our adaptation to a changing climate. Obviously, we need to be constantly improving our modeling and our resources for understanding our climate. Certainly, one of the things that we're concerned about is being able to tell the difference between an impact caused by climate and those caused by development and other human activities. We'd like to know what kind of strategies that we can put into place so that resource managers can manage their systems proactively, given what the uncertainty that we have in terms of the projections that we have for climate, both temperature and precipitation. And we feel that it's important to develop a cadre of trained resource managers that are going to be conversant in these issues as they enter their careers and able to carry through some of these adaptation implementations on into the future. And certainly one of the major problems that we've been encountering is, as I mentioned several times, is a lack of information, a lack of data. We also have a deteriorating system of surface and groundwater monitoring facilities, at least in Wisconsin. If we're going to be doing a good job of managing for climate in the future, we need to understand that climate better than we do, especially at the local level. And so these are many of the things that we feel we need to put more emphasis on society-wise to try and better understand our vulnerabilities and give us a better handle on how we're going to manage some of these climate impacts into the future. So I hope that this talk has provided you with a snapshot view of what we're doing in Wisconsin in terms of identifying climate impacts and adaptation strategies. There is much, much more that we have done that we couldn't possibly cover in today's webinar. I want to make sure that you all know that you can get a copy of our working group report on stormwater management, as well as the working groups on soil resources, agriculture, water resources, coastal communities, Green Bay, etc., as well as a summary report that's just come out from Wiki called Wisconsin's Changing Climate Impacts and Adaptation. All of these resources give a much fuller picture of the approach that we've taken to identifying what we expect from Wisconsin's climate in the near future and how we expect society to manage that successfully. And I think with that, Ann, I'd be happy to take some questions.
Okay, great, David. Thanks. And thanks to everybody who submitted some questions. I'm trying to look for the ones that overlap or deal with a couple of different issues. So we'll start with this one. Do you expect changes to occur quickly enough to start using climate models for sizing infrastructure, or should managers just keep using historic data for their decisions? And we had a couple of questions on the accuracy of those downsizing models.
We have talked with a number of system managers about that question, and I think there's two things to keep in mind. Many of the stormwater management facilities that are being designed today are being designed to meet regulatory standards that are based on those statistics that will need to be changed, but that change process will be very slow and deliberate. In Wisconsin, we don't expect to see anyone adapting newer stormwater statistics until NOAA Atlas is available in a couple of years. In the meantime, though, by raising the awareness of managers about these issues, what we're hearing is that when it comes time to make a decision about whether to put in a 12 or a 14-inch culvert, they're leaning towards the larger size. That they feel that they want to be conservative and they want to err on the side of public safety, and this provides more evidence that that's a good strategy.
Okay. Thanks, David. We'll go directly to an economic question. We had someone ask about the cost-benefit information that might be available regarding sanitary sewer overflow impacts and subsequent adaptations.
I would direct people to the Milwaukee Metropolitan Sewerage District website and to look under CSO, or Combined Sewer Overflow. They have put forward a report that describes the process that they've taken in trying to control those overflows and the costs that are involved. I think that the cost-benefit calculation is something that every community is going to end up doing for itself, and that there's not a one-size-fits-all approach to evaluating that.
Okay. We'll go to impacts in another stormwater management question. How is the increase in high water events likely to affect places where waste is stored? You mentioned sewers, but they were asking additionally about runoff from landfills or even nuclear waste storage.
Well, I think that's a really good idea. We've talked about things like petroleum storage in floodplains, chemical storage in floodplains. We had a problem in Reedsburg where LP tanks were shooting down the river near natural gas lines that cross the river. I think it's going to mean that we have to take a much closer look at our potential high water floodplains and what's actually located in those floodplains to be able to understand what the vulnerability is. And aside from a residential or commercial building impact, for example, that FEMA might do, I don't think that there's a very good sense that we have a handle on exactly where all those potential hazards might lie.
Okay. We have a couple of outreach-related questions. Does WICI have an Illinois or Midwest counterpart? And are some of the downscaled models available for other states?
I'm going to refer you to Dan Vimont, V-I-M-O-N-T, who's part of the WICI Climate Working Group. Dan is working with several other states to expand the range of those downscaled projections to an area that encompasses the Great Lakes states and actually a little bit larger than that. In terms of an approach, though, WICI really is the first of its kind, at least in the upper Midwest, and we're expecting that other states are going to follow the lead as they see the value of the approach we've taken of vulnerability identification, impact analysis, and adaptation development.
Okay, we'll get to some specific BMPs. Is there a list of currently acceptable stormwater BMPs and their potential impacts that you would recommend?
Well, I think EPA has a very good stormwater BMP webpage, an actual manual for municipalities. I would certainly send you to that one. I think a question that follows on that, however, is what is it you're trying to accomplish, and what exactly are the vulnerabilities of the different BMPs to these changing climatic conditions? If you're looking at trying to infiltrate water, which is a very popular approach, especially distributed in residential neighborhoods with rain gardens, for example, we're concerned that prolonged periods of rainfall, high groundwater might have the impact of flooding out those types of infiltration BMPs and killing the plants, for example. We certainly would hope that any new stormwater detention devices, whether they be ponds or whatever, are designed with these larger events in mind so that they can safely pass heavy water that is beyond what they are designed to contain. So those, I think, are some of the important questions that municipalities need to be looking at as they design their new stormwater BMPs.
Just going back to outreach, David, people wanted to know where they can get information on the climate models you discussed and if the resources are available at a website. Absolutely.
If you go to the Wiki website and look under, well, actually, on the very front page right now, there is a link to the full Wiki report. And then under the Wiki report, there are links to each of the working group reports, and you'll want to look at the Climate Working Group report, which gives you the details of how the downscaling was done.
Okay, and we can also link to those on the changingclimate.osu.edu site as well. I want to go back to a couple of big picture questions we got. Given it that each state has varied ways that they look at climate change, are there any plans for gauging stormwater management across the region or more of a comprehensive analysis?
Well, you know, that's interesting. Certainly some of the national organizations like the Army Corps of Engineers are looking at what you would expect the impacts to be from runoff on these large river systems that cross boundaries between states, the Red River, the Mississippi River, the Missouri River. However, as far as I know, most of the stormwater management regulations are state by state. And so while water quality might reflect EPA national discharge standards, quantity is not often regulated. In Wisconsin, we don't have any statewide regulations on managing stormwaters for quantity. That is actually devolved down to the local municipality. So I think it's going to be important to have a regional awareness and education on these type of issues, especially with the engineering practitioners that are generally the ones that are designing these facilities and working with the municipal managers to get the best response that we can.
Okay, we'll go back up to a science question. Somebody asked about natural versus human influence regarding some of these changes you discussed. If you could discuss that briefly.
A good example would be the Root River that runs through Racine, Wisconsin. Racine has been seeing higher and higher floodplain levels over the last decade or so on the river. And the community needs to know, is that caused by a change in climate, or is that caused by increasing exurban development in the watershed beyond the boundaries of Racine? And so those are the types of trade-offs that we talk about. Another would be, of course, you know, a wetland situation where you might have previously drained wetlands. What is the impact of that drainage system on the wetland structure in a changing climate versus one where the drainage system has been removed and the wetland has been restored?
Okay. We're going back to economics here, and we have a question about the cutoff on the risk benefits of long-term reconstruction, and specifically the question relates to should planning be done on a 100-year storm or 500-year? And then just an extension of that, what about getting citizens to pay for removal of CSOs?
Okay, so a couple of things. Let me just start out by saying that it's, in terms of adapting to climate, the climate changes that we are projecting are long-term, but many of the infrastructure decisions that we make are not as long as that. So a wastewater treatment system might be making decisions for infrastructure that's going to be in place for 50 years, whereas a suburban development might have a much shorter planning horizon. That's something that we need to think about a little bit. Certainly, when we're talking about disconnecting from combined sewer overflows, it's going to be the community that's going to decide how that's going to be paid for, whether the homeowner is going to do it or whether the wastewater treatment facility is going to do it and then charge back to the entire system. So those are some local questions that I don't think that we have specific recommendations for.
Okay, well, you mentioned homeowners, David. We had a question that just came in about changes the average citizen can make in their own home to address some of these potentially new trends in rainfall or flood events.
Well, I think that you should first of all understand where your house is in relationship to a floodplain. Secondly, you should understand what happens with stormwater on your property when it does rain hard, which I'm afraid means going outside in the rain and getting wet and looking around when it's coming down. For most homeowners, especially if you're on a sanitary sewer system, you want to avoid rainwater entering your basement and going into your floor drain. And if you have a roof downspout that goes into a drain that goes into the sewer, you want to disconnect that and run it off into the street or across your lawn if at all possible. You can certainly do more than that, putting in a rain barrel or a rain garden to capture some of the contaminants from smaller storm events. And there are many, many good guides out there for residential stormwater management.
Thanks, David. And then we'll take, I think, two more questions. One is on actual costs, how a particular cost was calculated. We had a question about the calculation of $7,500 per residence for downspout disconnection. I'm not sure what that related to, but if you want to just speak to the in general, how those are calculated.
Well, that was an estimate that came from the Milwaukee Metropolitan Sewage District for disconnecting the downspouts and I believe closing the drains that led from the surface into the sanitary system. And that more information would be available on that either from the Milwaukee Metropolitan Sewage District, or if someone wants to contact me by email, I can send them some specifics on that.
Okay. And then just a final question on the idea of outreach to other institutions. Someone asked if this information will be shared with US EPA, especially as they're looking at negotiating with cities dealing with CSOs.
Yes, certainly, and I know that the McClellan Group in Milwaukee is actively engaged in that process, and that is where this information came from. And
just as we're getting ready to conclude, David, a couple people have again asked about equivalence to the Wiki group in other states. So if you could just speak to that again.
Well, I hope that if you're planning on putting together a group to look at climate impacts, that you'll take time to look at the model that Wiki used. It's been very, very successful. We have been very collaborative and collegial, and I think that one of the things that we've done is to educate ourselves as we begin to educate others, and that's a very powerful approach.
Great. Well, I really want to thank David again and all of our participants for the excellent question and answer session. Just as another reminder, this presentation and the related education materials, including those links David mentioned where you can get to some of the information he presented, will be available at changingclimate.osu.edu. And we've got the survey posted now. It's on SurveyMonkey. Please go to that link in your chat box and fill out a very short evaluation. about today's webinar. And I really want to put a plug in for the next webinar on March 1st. This has been a really fascinating topic, and the next one will be related to the economic implications of climate change to the Great Lakes ports, harbors, and marinas. This may be of particular interest to you that are working in stormwater infrastructure, because they'll be looking at a matrix that can be applied to calculate current value and future liability of stormwater infrastructure with a changing climate. I also want to point out that the registration is now open to that webinar and will be posted again in the chat box if you want to also go ahead and register for that one. We really want to thank David and all of our participants today. This concludes our call. We hope to have you here again on March 1st at the same time for the next webinar. So thank you, David, and everyone, and have a great afternoon.